Hello, everyone. Welcome back. We're coming towards the end of the conference here, and so I want to welcome everyone to the session Data Flow Parallelism for High Energy and Nuclear Physics Computing Frameworks by Kyle Koneful, Saba Suresh, Mark Paterno, and Chris Green. I'll turn the session to you all.
Thank you very much, Sri. It's a pleasure to have the opportunity to talk with you about data flow parallelism and computing frameworks. And before I talk about the computing challenges we're facing, I want to set the context first, and that's talking about the science. So what is the science we're dealing with here? Well, Mark, Saba, Chris, and I work at Fermi National Accelerator Laboratory, affectionately known as Fermilab. It's about 40 miles outside of the city of Chicago in Illinois, and it is America's particle physics and accelerator laboratory. In the US, there are other laboratories that have particle accelerators. However, Fermilab is the only US laboratory whose primary focus is particle physics. In this picture, you can see two large accelerator rings. The ring in the background is called Tevatron, and about 15-20 years ago, it was the highest energy particle accelerator in the world before the Large Hadron Collider came online in Switzerland around that time. So the Tevatron is no longer used at Fermilab for accelerating particles. However, the ring in the foreground is still used. It's called the main injector, and it is used for creating particles like muons and neutrinos, which we'll talk about soon. So another thing I should mention is that Fermilab does not do nuclear physics experiments per se. So although what we're going to talk about today has a lot of relevance in the types of data processing that are done in nuclear physics circles, we'll be primarily focusing on particle physics. So what is particle physics? Particle physics is exploring nature at its most fundamental level. As far as we know, matter is composed of quarks and leptons. These are very, very tiny particles. Quarks come in 6 different kinds. We have an up quark, a down quark, charm, strange, top and bottom, or depending on where you live in the world, you might say truth or beauty instead of top and bottom. They're creative terms. If you take a couple of up quarks and then combine it with the down quark, you get something called a proton. And if you take an up quark and combine it with 2 down quarks, you get something called a neutron. So these are things that we are familiar with. You can then take protons and neutrons and combine them together, and eventually you get atomic nuclei. And it's the exploration of those nuclei, which is really the focus of nuclear physics, which, as I already mentioned, I'm not going to focus on too much. At Fermilab, we're interested in looking at the quarks as much as we can themselves, but there are also things called leptons. And you're probably familiar with one of those leptons, which is called an electron. It comes with some companion particles. One is called the muon, and one is called the tau particle. There are also then companion particles to those called neutrinos, and I'll talk about neutrinos soon. So in addition to the particles that make up quarks and leptons, there are also particles that convey forces between the matter particles. And one of those particles that conveys forces is called a photon, which you've probably heard of. Not only is the photon the particle of light, but it is also used for carrying the electromagnetic force. There are a handful of other particles that you see there that convey force. And at the center of all of this is something called the Higgs boson. I won't go into what the Higgs boson actually does, but it is a crucial component of the theory of particle physics. And in fact, about 10, 12 years ago, the Higgs boson was actually discovered at the Large Hadron Collider in Switzerland. So how do you actually look at these particles? In order to get there, you need to accelerate larger particles like protons to very high energies. When you get them to very high energies, they end up traveling at very, very close to the speed of light. the collisions that result give you some byproducts, some other particles that come out of those collisions, and those byproducts are very, very small in the fundamental particles that we're interested in. Because it takes such high energies to accelerate those particles, this field is called high energy physics. So I mentioned we'll talk about neutrinos. As you saw in the previous slide, neutrinos come in 3 flavors. They have no electric charge. In addition, neutrinos fill the whole universe with about 10 million of them per cubic foot, and most of them zip straight through the Earth and through particle detectors without leaving a trace. Because they almost never interact with matter, only massive and sophisticated experiments can catch and measure the properties of neutrinos. In addition to neutrinos having no electric charge, they're very, very light. They travel at close to the speed of light, and it's possible for one neutrino to turn into a different flavor. What you see on this wave-like curve is the probability of, once you've created an electron neutrino, what's the chance of observing it as an electron neutrino as it travels over a certain distance. So in fact, at some distances, what may have started as an electron neutrino will no longer be an electron neutrino at all. It might be a muon neutrino or a tau neutrino. How this all happens and the location of these peaks and troughs in this wave is an active field of study. So how do we actually detect these neutrinos? It's difficult. You can't directly detect a neutrino. They're pretty much invisible. However, if you have a detector with enough material, in this case, we'll think of liquid argon, you will eventually detect a neutrino interaction. So here is a picture of a neutrino interaction in a detector at the microboon experiment at Fermilab. You can't actually see the neutrino, but that dotted line that says neutrino above it is the inferred trajectory of the neutrino when it went into this microboon detector. What you can observe is that after the neutrino has interacted with the argon nucleus, you get a bunch of particles that come out of that interaction. In this case, 4 protons and 1 muon. So it's that interaction, or the byproducts of that interaction, that you use to infer neutrino properties. At Fermilab, further neutrino study will be taking place in a very large experiment called DUNE. And the goal there is to investigate these neutrino interactions much more precisely than in the past. So I'd like to tell you a little bit about the DUNE experiment. It is large. It spans multiple states. So you have Fermilab in Illinois on the right side, and it is the responsibility of Fermilab to create a beam of neutrinos, send that beam through the Earth all the way to South Dakota, where neutrino interactions are observed there. Now, you may notice that there are actually 2 detectors here that are required. Remember, I discussed that we want to see how one neutrino oscillates into another one. To do that, you have to figure out what you're starting with and what you're going to end up with after that neutrino travels through the Earth. So you have a near detector that wants to make sure certain properties of this beam that's created all these neutrinos. It's a complicated device, and it might be difficult to see the tiny person that is on top of the box-like structure on the right, but you can get a sense for the size of the near detector. That's a crucial part of the experiment. However, in South Dakota, there is another detector, which is much larger, and you can see 2 people there in the corner having some type of conversation, and it is this far detector that can then be used to determine whether these neutrinos oscillated from one kind to another. In addition to learning things about neutrino oscillations, the DUNE experiment will also be able to detect neutrinos that occur from supernova. So a supernova appears in our galaxy. It's predicted to be about once a decade. And a supernova is simply the collapse of a very large star. Whenever that happens, the first thing that is emitted from the star that has collapsed is a wave of neutrinos. And that happens before the photons or particles of light are emitted several minutes later. Because the neutrinos are emitted first, if you have a neutrino detector like DUNE that can detect the neutrinos, then whenever it makes that detection, it can use that information to tell the telescopes around the world where they should point their instruments so they can observe the supernova once it actually becomes visible. So depending on where supernova occurs, DUNE could detect anywhere from hundreds to thousands of neutrinos. The amount of data that is recorded by DUNE whenever supernova occurs is somewhere around 1.5 terabytes per second, which is a lot of data. Now, DUNE is not going to record 1.5 terabytes of data per second all the time, but whenever it detects something that seems to be consistent with the supernova, that's when it opens up the data gates and then starts trying to track as much data as it can for about 100 seconds. So that sets the context for what we're interested in exploring scientifically. Now, how do we actually look at these things from a computing standpoint? So let's talk about processing the data. The detector detects what we refer to as the data. And when we're talking about real data, well, that's just simply data that comes from real physics processes, either from the neutrino beam that I discussed earlier that shot from Illinois to South Dakota, or it will detect neutrinos from supernova. However, when it comes to computing, we also have to simulate the data to make sure we understand everything as much as we can. There are different stages of simulation. There's a physics generation stage where you take the mathematical descriptions of quantum mechanics and how those descriptions correspond to actual physics processes, and then you simulate a detected event, for example. Or in this case, it's just a collection of particles that are randomly generated, probably at the center of the detector. Maybe it's in the corner, who knows? But once you have those generated particles, you then need to propagate them through some model of the detector. So you can make sure you understand that the interactions of the particles with the detector are happening according to what you think should happen. Not only do you have to simulate those things, you also have to simulate the actual signals that are recorded by the electronic systems in the detector. So it's a complicated series of simulation steps that have to take place in order to make sure that you understand the detector at the level required to make inferences about physics. How much data are we talking about? For real data, whenever you're talking about beam data taking, DUNE expects to see about 6 gigabytes per detected signature that is consistent with the neutrino interaction, where a signature is just basically some interesting characteristics of what's detected that might look like a neutrino interaction. The number of times the experiment will actually see something consistent with the neutrino interaction, it depends on if you're looking at the near detector or the far detector. However, once you go to the far detector, which is very sensitive to supernova type physics, that's going to happen very, very rarely. Whenever that happens, it's going to read about 150 terabytes in 100 seconds. And the prediction is that it will have to process that data within several minutes to be able to guide optical telescopes where they should look for the supernova. Now, although an actual supernova is very rare, DUNE expects it will see signatures in its detector that are consistent with the supernova about once per month. DUNE will also want to test that its structures are prepared to be able to handle all that much data. So they want to test it about once a month for that reason as well. In terms of simulated data, the amount of simulated data is much, much larger than the real data. And the reason for that is you cannot just simulate your physics of interest, neutrino interactions, for example. You also have to simulate every kind of physics you can think of that mimics real neutrino signatures. In addition, quantum mechanics is based on probabilities. You are not guaranteed to have the same outcome every single time. So in order to make sure you understand things well enough, you have to simulate many combinations of different outcomes so that you can understand the types of complications necessary in analyzing your data. So you have physics that has created data, and from that data, you want to infer what happened to the physics. In order In order to infer what happened, you have to account for the real data from detector signals, the detector signals from real physics. You have to account for details in the neutrino beam that was sent from Fermilab to the detector in South Dakota. You have to make sure you understand the detector geometry. How was the thing put together? What happens if you have a crack in this corner of the detector and a particle goes through it? Do you understand how that might affect how well you're able to register the different kinds of interactions that are of interest? Then you have calibration information that account for many imperfections. There are environmental conditions, temperature, air pressure, magnetic fields. All of those things have an effect on how you detect the data. Once you've accounted for all those things and found ways to combine them at the right points in your programs, you can then start identifying interesting physics. But you got to do that for all your data. You have to account for a lot of junk that nobody really cares about, but is there anyway. It just sort of pollutes the signatures of interest. And then you can actually analyze what's left and publish your results. So the question is, how do you do this? How do you express this as a scientific workflow, where we're defining workflow to just be some kind of program or set of programs that executes physics-based algorithms in a certain sequence or graph. So what does that look like? Here is an existing workflow used by the DUNE experiment right now. DUNE is not yet operational. It tends to start collecting data in a few years. DUNE is looking at many, many simulations. The purpose of this slide is not to read any of the characters on the slide, but it is to gain an appreciation for all the physics steps that must be performed to do a physics analysis, and to see the dependencies of one step with respect to another one. So each oval that you see here corresponds to an algorithm that is crucial to the actual processing of the data. And all the boxes that you see here are actual data that either serve as input to the algorithm or output from the algorithm. One of the complications is that each of these algorithms is written by a different person, most likely. So you will have many different algorithms coming from many different physicists with different skill levels, different understandings of how best to use the computing architecture they have available to them, the computing languages that they have available to them, and then finding a way to orchestrate this entire workflow in an efficient manner is quite a challenge. One of the other things that we have included as part of each of these algorithm nodes, if you like, is the time it actually took to execute the algorithm once. And for one of these algorithms, it can take 70 seconds. That sounds like a long time, and it is. However, it's actually much worse. There is a very wide range of algorithm execution times ranging from tens of microseconds to 1,000 seconds. This is a very, very large range, and it is difficult to find ways to execute such a workflow efficiently. Unfortunately, the placement of these algorithm nodes doesn't actually reflect how the algorithms were executed. Plot, or in this graph, you see 6 algorithms that are right next to each other, and they don't seem to have any data dependencies that are shared necessarily. In principle, they could be executed in parallel. Unfortunately, due to limitations in the current computing model of the framework that I'll talk about in a little bit, they can't be executed in parallel. They have to be executed serially. So this is another limitation that you cannot see just by looking at a graph of data dependencies. In addition, you cannot see that there's often mutable state that is updated when executing an algorithm. Remember, these algorithms are not created by computing professionals. These algorithms are created by physicists whose primary expertise is physics. They have to learn the computing in order to get done what needs to be done in terms of analysis work. But that means there can be practices that are adopted that are not necessarily conducive to efficient computation. Handling mutable state is a good example of that. Also, each of these algorithms may have a filter that is inserted in front of each of them. It may be that you don't want to look at all the data that is coming from the detector, but only some of it is of interest. So you would put a filter in front of these things. This graph doesn't show that. This graph only shows one level of the computing hierarchy. It could be that there are many different kinds of graphs like this corresponding to different signatures that were detected by the DUNE experiment. And then at the end of the day, the results of executing all those graphs has to be pulled back together into another graph. You don't see that complexity here. You also don't see that data are generally written to an output file so that that data can be used for subsequent processing. You don't see data dependencies that are implicit from accessing global data. And you also don't see that there is serialization required for some nodes that access shared thread unsafe resources. So all of this is a challenge for us, and we're trying to figure out how to handle this. So the takeaway from looking at this complicated graph is, as complicated as it may seem, it's much worse than what's actually depicted. And there are many, many more like this. So how are we going to go about improving the situation so that we can leverage the technology that's out there now while still making it possible for physicists to easily plug in their algorithms into a framework that is intended to orchestrate how those algorithms should execute? So the first thing we did was to look at how the data are actually organized. So in high energy physics, experiments tend to group data into a hierarchy. For example, you may have a run which corresponds to all the data collected in one day. Within that run, you may then decide to split up your data according to all the data collected for each hour. So you might have 24 subruns per run, one subrun per hour. And then within each hour, within each subrun, you might have many events. And it's the events which correspond to the small bits of time where you actually saw something of interest in your detector, and you want to see what you get from processing the data from that neutrino interaction. So there's a hierarchy then of data here. In high energy physics, when we're talking about certain data members of a data set, we refer to those as data products to distinguish them from other types of data that physicists have to deal with. So on the subsequent slides, you're going to see a progression of how data residing in one run, which is just labeled R, can be processed more finely by splitting it into subruns and then events. And each data product you see is represented by one dot. Okay, so here's a run with some data products. These are just bits of data. What they are not really important right now. And in reality, you would see many, many, many more dots than this. But this is just to illustrate the types of things we're dealing with. Usually there's not enough memory on the systems physicists are accustomed to using to be able to process all the data in one run at one time. So it is convenient to split up that run into subruns. So you can now see that I've split up most of the data of the run into 4 subruns. You do have some data that correspond only to the run, and those might correspond to basically summaries of everything in the subruns. And I'll talk more about that later. That has to do with folds, but we'll get there soon enough. In practice, subruns are still too coarse of a grouping of data to be able to process it efficiently. So the subruns themselves are then subdivided into the events. So this is just showing in picture form what I already said on a previous slide. Now, if you look carefully, you might start to see some regularity between these events. Typically, what happens in high energy physics experiments is you try to express the data you see consistently across the events that are recorded. So you need to be able to label each of these things. So each data product tends to get a label. That way physicists can zero in on the actual data of interest. And then just for the sake of discussion, I'm going to get rid of most of the dots and label the other things. Okay, so this is is a very data-centric way of looking at things. And this is how we want high-energy physicists to start thinking about their data, not thinking so much of the procedure of how do you manipulate from one piece of data to another, but we want them to think about the data themselves. After all, it's the data from which you actually get interesting physics conclusions. So in order to go from one piece of data to another piece of data, we have things called algorithms. So yes, the physicist still needs to write the algorithm that can transform one piece of data to another piece of data. However, we want to find a way for them to do this in a simple manner. Right now, they have to deal with a lot of procedural code, a lot of for loops, if statements, mutable state all over the place. This is sort of undesirable. It makes it difficult to glean what is supposed to be happening whenever you're looking at a large graph of nodes. So what we want the physicists to just provide are simple algorithms that transform data from one type to a data from another type, for example. It is the responsibility of the framework to then wire up all these algorithms in a way that the data dependencies are respected and in a way that physicists don't necessarily have to recompile all their code once they want to add another algorithm to the framework. No, they should be able to specify at configuration time, at the runtime of the program, which kinds of algorithms they want to execute. Now, we won't be naive. I mean, just having a simple transform is nice, but it's not generally the only type of processing that is done. So let's first look at what things would be once we start applying an algorithm, just a simple transform from A to B. This is what you would see. You see a lot of regularity here. But what happens if you want to then start creating summaries of data? Well, that's where we start getting into folds. So in this case, what physicists often like to do is to create things like histograms, which is really just an accumulation of data over the course of a sequence of data. You process each element of the sequence, and then you update your result. Physicists do this all the time without actually realizing it, because a lot of what they see is couched in very procedural code. Well, really what they're doing is just a fold. For the sake of DUNE, what they want to be able to do is not only look at folds, they want to look at unfolds, which is taking one piece of data and then essentially unfolding it, generating a sequence from that one piece of data. So DUNE wants to do both things, they want to do folds and they want to do unfolds. And the framework has to be able to convey those pieces of data from one algorithm to another algorithm in an efficient way, and in a way that makes sense to the physicists. So what we're really wanting to do is find a way to simplify this picture that you see here. There's a lot of regularity from one subrun to another subrun, from one event to another event. So instead of thinking of all these individual arrows and all of these individual boxes, you can aggregate things into something much simpler. So instead of thinking of processing single pieces of data, instead, we're thinking of processing sequences of data. And then the user's algorithm, the F or the G that they provide, is then invoked by the framework on each of those elements of the data. So what F here is corresponds to something called a transform, or a map. All you're doing is taking one sequence of data and then transforming it to another sequence of data of the same length. For the other kind of operation, we want to take a collection of data elements, C, and then transform them to a smaller collection. And in this case, because there's this hierarchy of data, we're going from all these events to something at a higher level. That's just a reduction, or it's a fold. It's a repeated operation that you keep invoking on the data until you obtain your final result for that subrun, for example. So what is this? We're just looking at a graph of higher order functions. So higher order functions. So in this case, it's transform and it's fold. The user really only needs to provide the operator to the higher order function. So for a transform, it's just f of a equals b. For fold, it's a little more complicated. You might take in the current result that you care about and then sort of append to it somehow or adjust it somehow. Or if we were really using a functional programming style, you might just return a new object. Regardless, this is a much simpler approach to processing your data than having to worry about a lot of mutable state and all the problems you have to deal with in terms of multi-threading and multiprocessing. Note that this does not actually specify an implementation. It could be that it makes the most sense to process one element at a time and then produce another element on the other end. Or maybe it makes sense to batch all the input elements together, offload the computation onto a GPU, and then transfer the data back to the CPU. It really depends on the situation, and you could have more exotic combinations than that. So how are we going to do this, though? HEP processing as it exists now is very procedural. It's not very functional. Is there a way we can process high-energy physics data in this way? So this brings me to the last portion of our talk, which is our collaboration with the oneTBB developers. And this is really getting at how do we move from this procedural way of thinking in high energy physics to a more functional way of thinking. So we did this by looking at oneTBB's flow graph, which seems ideally poised for handling the type of data processing that is in high energy physics and in nuclear physics. So it shows you can express data dependencies using flow graphs, nodes and edges, and it works all very smoothly. The trick, though, is figuring out how to rephrase all the existing high energy physics algorithms and processing behaviors using higher order functions. So in the last few years, we've been exploring this possibility through an R&D project called MELD. There's a prototype technology there. And what we discovered is that, yes, actually, using oneTBB flow graph's existing graph nodes, we believe we can support each processing idiom used by our community and more. Transforms are certainly straightforward to implement using what is currently available with FlowGraph, but there are additional features that would directly benefit the HEP and nuclear physics community. So we proposed new nodes to oneTBB's FlowGraph. One is the fold node. This is just a node that supports a reduction operation or fold operation. It would accept many messages, so where each message is an element of the sequence, and each message is input, but then the responsibility of fold node would be to output the fold result, or the result of performing that reduction over the entire sequence. The implementation is tricky. We have internal counters that we put in place to ensure that the reduction result is emitted once the full sequence has been processed. And that's kind of tricky because we're talking about multi-threading, and it's things don't necessarily appear in order, but yet it's doable. We've also proposed something called a serializer node, which handles the case where you have a thread unsafe library that has to be invoked from multiple nodes. oneTBB's flow graph allows you to specify concurrency of one for each algorithm. So a given algorithm will not be invoked concurrently, but in high energy physics, we need something more than that. Not only can one algorithm not be invoked concurrently, if you have n algorithms that all rely on the same thread unsafe resource, though none of those can be invoked concurrently. So we have to be able to serialize access to that thread unsafe resource through something called the serializer node. And that's just using the token-based system that already exists in oneTBB flow graph. Okay, I mentioned filters. We don't always want to look at all the data. In fact, discoveries in high energy physics are made based on looking at subsets, usually very small subsets of data. So how do you implement a filter using oneTBB flow graph or using higher order functions in general? It's kind of tricky. In general, you have a predicate H, which the user or the physicist would supply. It's just a transformation that takes input data and yields a true or false value. But how are you actually going to use that? Well, it's a little tricky. And this graph actually does show how you can go about doing that, but it's not obvious at first. So it does take some thinking. So how do we tackle this? Well, early this year, we started a series of meetings, and I shouldn't say we, but we, not as in Fermilab, but there was a joint Fermilab Intel effort that started meetings to look at these issues. So after our first meeting, we started to propose some ideas. So we first proposed the graph serializer nodes, and shortly thereafter, we received a thorough analysis of our ideas and what could be improved on our end, and whether there were things on the TBB side that could be improved. This was very, very fruitful and exciting for us. So we continued. We then proposed filtering. Same story. TBB developers got back to us and said, well, maybe we could try it this way. So there was a back and forth that was pretty regular. After we did filtering, we then looked at reductions. And then again, the oneTBB flow graph developers gave us their analysis of what we had done and what possible improvements could be made. And we're now at the point where we're starting to make high energy physics benchmarks where some of the TBB, the oneTBB ideas could be tested. So what is the outcome of this? From the beginning, we had very active interest from Intel in our needs. And the oneTBB flow graph developers thoroughly reviewed our ideas, identified some weaknesses, and suggested some potential improvements to our own use of TBB. Some ideas, though, have also motivated potential improvements to oneTBB. And one of those ideas have resulted in an RFC that is being formed to look at adding a full node to the flow graph. So we are very excited to see this development. Everybody benefits, not just Fermilab, not just Intel, but the UXL community benefits. Anybody who needs to deal with this type of scientific processing can benefit from this development. So we are very excited. The oneTBB flow graph is a promising technology for meeting data processing needs of the DUNE experiment, the high energy physics community, and also, we believe, the nuclear physics community. We've had very productive interactions with oneTBB developers, leading to our better use of oneTBB, and potential improvements to oneTBB itself. We are encouraged by Intel's desire to engage its user community and very encouraged by the openness of the UXL RFC process. So you, like us, can influence the development of things that are in the oneAPI spec.